We are now beginning one of the more important sections of this chapter, which is actually understanding the ideas of how we go about talking about the fields from extended objects. So these are not objects that can be simplified down to point charges. Now there's a few preparatory things I want to discuss that will help the rest of the videos make more sense. So first, whenever we're talking about these objects, and two examples here are a line of charge and then a sheet of charge, is that we're assuming that they're uniformly charged. And all that means is that the charge in one area, if it had the same size, is the same as the charge in another area if that had the same size. So if I only take a segment of this line of charge with length L1, and I look at the amount of charge only on that segment, not on the whole thing, and I compare that to a different segment with length L2, and I then look at that charge, if the length of L1 equals the length of L2, then you have in fact a charge Q1 equaling charge Q2. So this should make sense. That's like saying if I have a big bag of sugar and I take one handful of sugar from one part of the bag and a different handful of sugar from a different part of the bag, that it would really be the same mass of sugar. So this is actually the idea of a density. But since this is a length, we're actually going to be talking about what's called linear charge density, and I'll go through that in more details next. But then the same rule applies for the surface charge, that you can see that these are equally spaced. Again, if we take one little area in one place and compare that to the same sized area in another, you would have the same amount of charge. So the idea of talking about an object being uniformly charged is that the charge has equal spacing. You don't have all of your charge in one area and very little charge in another. In general, we're going to talk about uniformly charged objects. It's going to be pretty reasonable to assume most of our objects in the real world that we're going to be doing calculations with are like that. There's going to be a few problems in the book, not necessarily ones that you're assigned, where it might be possible to do a calculation where there actually is a varying charge density, but that gets very mathematically complicated very quickly. So in many problems, we're going to say that the object is uniformly charged, meaning that you have this equal charge distribution. And when you're working with a real-world problem, you'll want to simplify or approximate it as being uniformly charged so that you can use these ideas. So what is linear charge density? If we have a finite length of an object, and again in this case we say that this is a line, meaning that we don't really worry about how wide this is or how thick it is. It's described by one property, which is its length, and we can say that it has total length L and total charge Q. So to calculate the charge per length, you just divide total charge by total length. And this gives you this quantity called linear charge density. This is the Greek letter lambda. So linear charge density describes how much charge you have per length. So the upside is that if I have a known tiny amount of length, delta L, now in mechanics we usually use delta to mean change in. Here we are also using it to mean a tiny quantity. So you can think of this also as being like instead of using the lowercase Greek letter d, delta, so lowercase, which is just moving towards talking about an integral quantity, dl. So that's all we're doing. So delta here isn't change in, it's just a very small quantity. So if you multiply that by your charge density, you get how much charge is on that segment. So one thing to note here is that if you have a finite length, then you have a fixed value of charge and a fixed value of length. If it is infinite, which is going to actually happen more than you might realize, then you actually have an infinite amount of length and an infinite amount of charge. So you can't just divide those things. So in this case, we must use these deltas, where again, you can think of this as effectively being dq over dl, right? It's not change in length or change in charge, it's a tiny amount. So this is a different way to just write the same idea. We're not quite in the infinite limit yet, but that's what it would become. So in some cases, you were going to have an infinite wire and you're going to be told what your charge density is, your linear charge density, and just go with it. Don't try to calculate your total charge because you'll get an infinite amount of total charge because you have an infinite length. Very similarly, we have surface charge, which uses the Greek letter eta, and that's going to be charge divided by an area. Now again, delta is just meaning a tiny amount. So we can again get the amount of charge in a total tiny amount of area by multiplying it by the surface charge density. So we call this eta surface charge density, since again it's telling you the charge per surface area. Again, we're frequently going to work with infinite planes of charge, and so in that case your total charge is infinite, your total area is infinite, but we can actually still define a surface charge density based on a tiny amount of charge and a tiny amount of area, where in this case, again, these are well-defined quantities. So you need to be able to recognize the notation we're using and ideally use that notation in your problems, eta for surface charge density, lambda for linear charge density, since that's one of the ways you'll be able to identify equations and use them on the equation sheet. So a few concluding comments. You might see sigma used for surface charge density. So in the book is going to use eta, I will use eta, but other books might use sigma, and so if you're looking online at other resources, you might see sigma used, but I'll try to be consistent in using eta. The units of these two things are different, of our linear charge density and our surface charge density. Remember that C stands for coulombs, and that's the unit of charge. So if we're just dividing charge divided by length, you get charge per meters, and charge divided by area will be charge, coulombs, per meter squared. There is a quantity called volume charge density, and we use the Greek letter rho, which looks like a P, and this is also the letter you typically use for just defining normal density, so mass density, but in this class we rarely talk about mass density, and we normally talk about, well, we more frequently talk about volume charge density. So that's going to be the amount of charge divided by the volume. Again, in certain situations it could be infinite. So this is a quantity we'll talk about more in chapter 24, but just be aware that we do have line, area, volume. So one-dimensional, two-dimensional, three-dimensional.